Hello. So je n'ai pas clicked. Anyway, so hello everybody. My name is Emna, and I am honored today to present to you our work on adaptive UDP video streaming, which is a hybrid resolution control and perceptual enhancement kind of project. It touches on low latency adaptive networking, on AI super resolution, and it is a quality of experience aware streaming. This work was developed alongside my colleagues at University of Mercy, Evan and Jing Wang, and our dear professor, Dr. Otaiba Mohammed. So let's dive in. We see today, we're watching a lot of videos. We see them over YouTube, we watch them on Netflix, and a lot of these big names. And because of this unstable bandwidth and jitter, we get to see this moving circle that everybody hates, right? So, what's wrong? These approaches use TCP and dash based streaming, which introduces this latency because of the reliability and all these handshakes. And we see the alternative is UDP. UDP is a best effort protocol. It doesn't really care if you get it all. In videos, really, we don't really care if we lose one frame. So UDP prioritizes this timelessness. And other than that, we see that low resolution also reduces this heavy load that you're trying to push over your network, but it also reduces perceptual quality, which is something that we don't really want to see. So, what are we trying to do? We can combine that with a client side AI aware to enhance side like client to enhance this quality and restore the details of this bad quality. And that is what we tried to do. So as you can see in the bottom, there's something that's moving. What is that? That is actually our work. It's a proof of concept video. We tried to take that in the winter. You can see it's cinematic, it's beautiful, but it was just like a short video that we're looping right now. So we can see a lot of packets being sent. And you can see it starts off with being 1080, and then you can see that upscaled plus sharpened. That's what the client side, when it receives this for 80, that's how it upgrades it. And it doesn't look too different from the previous frames. So that's what we tried to achieve. So moving on, we coming up with this system, we try to analyze existing systems. We understand what's happening. So we looked at the networking side, and that's where we looked at the adaptive bitrate streaming. We see that dash-based ABR systems rely on TCP delivery, just like we said, which introduces buffering latency in real-time applications, and that has been discussed a lot by a lot of researchers, and even like on standard, we know that. And then we explored how can we like move on off of that. So we saw that Spiteri et al. From the papers that we've read used this buffer-based method such as BOLA, and we also explored Pensive, which was also discussed by Mao et al., which improves this adaptive bitrate selection. So there's a lot of approaches that we can use to make sure that the network is we're getting our frames without with overcoming these challenges of the actual transmission. So what we tried to adapt from that, we adapted the buffer-based method. We added a small buffer so we can keep on displaying frames even if we don't have as many coming just because of this latency. So we're including that, and we're adapting a lightweight UDP to overcome the TCP challenges with it being reliable, etc. And we're switching resolution, and then we're also using perceptual enhancement. But what kind of perceptual enhancement? That's where we read about the quality of experience. We wanted us and the viewer to have a good experience while watching videos. We don't want it we don't want quality to drop suddenly and you're looking like, what's happening? So what QoE, which is the quality of experience, actually studies, it evaluates this user perception through metrics such as the delay of the startup, the rebuffering, how much or how long do we see that like circular thing, and what's the variation, what how good, how bad it is. And prior studies show that the resolution does really affect the viewer. And that has been studied in a lot of papers that we mentioned here, Zinner et al., Hopefield or Hopefeld et al. And what we try to do is we try to study that in our work, and we're evaluating this through latency, playback continuity, buffering behavior, the way we perceive it, but we're also employing quality assessed values such as the peak signal to noise ratio and the structural similarity index measure for this object comparison of enhancement modes. Obviously, they don't really have to always match what we see. Our eyes are actually more of a have more of this value, but we also need metrics. We need values to assess our model. And then we looked, okay, we want to enhance this lower resolution frames that we're trying to send. So how are we doing that? We looked over super resolution enhancement, which was discussed by a lot of other authors. And Dong et al. Explored this fast super resolution CNN. And that reconstructs this high quality resolution frames from the low resolution inputs. And we chose this one because it employs a very practical real-time inference in this low resolution frame feature space. And so we have this alternative to transmit low resolution, which would optimize our throughput, our how we deal with a congested network, but also enhances the receiver experience. So we try to integrate three different approaches. One of them is the super resolution through the FSR CNN, fast super resolution convolutional neural network, but also using bicubic and using fast API, which is on a different server. So how is our work? So this is an overview of our system. We start on the server streaming. We have pre-encoded videos on 1080 pixels and 480p frames over UDP application layer fragmentation. So we take the frame, we fragment it, and then on the client side we reconstruct, we decode, and we render frames into the playback queue to be displayed. If the image is low resolution, that's when we send it to bicubic, FSR CNN, or the server assisted enhancement through FAST API. And then we have this bidirectional feedback. Just like we said, we have the buffer. Oh, what happened here? Sorry. We have the buffer. So we're using BOLA. And then, so we're sending the buffer occupancy grid, which is how many frames are actually in our buffer right now, just to correct maybe the server counting, which we're going to get to. We have the frame rate, and the server uses the RTT, getting back to it, to do the throughput estimation. And we have this dynamic resolution switch where the server adapts this RTT and the RTT based throughput, and using a hysteresis mechanism to dynamically switch between 1080 frames and 480p frames. So diving into the system more, we have the protocol and the packet design. To be able to implement this, we developed a custom lightweight UDP protocol for these fragmented video frames. We made a header of only 8 bytes, including the packet type, the frame ID. Frame ID is what enables the client to actually reconstruct the frame, the fragments, but also reorder the fragments, the frames, because we know frames can come just because of the UDP, they're not going to be ordered. So that is one thing. And then we have the fragment index, so we know where the fragment belongs. And then we have the timestamp, which would allow the server to actually have the estimation of the RTT, which is the round trip time, which we're going to uh, touch in a minute. And then we have the resolution flag, which would say high or low, and that enables the client to know, does this frame need an augmentation and optimization or not. For this, we're using a max payload of 1200 bytes, and that is to avoid the MTU, just to like be below the MTU thresholds and to avoid the IP fragmentation and to get reassembled at the client. So just like in the picture you're seeing, we have the frames, the packets moving from the server to the client. And once a frame is fully reassembled and constructed in the client, we send back this ACK with a timestamp. So the RTT estimation is when the server gets this time, the timestamp, it compares it to the actual clock right now, and it gets the RTT estimation. Obviously, it's a conservative RTT estimation because it doesn't only take the travel time, but it also takes the reconstruction time. And we were okay with that because we'd rather overestimate how bad the network is rather than underestimate it for our system. And that's how the server later calculates the actual throughput. So the server design for the RTT-based throughput, it's the throughput is just the load over the RTT in our system. And then we have the exponential moving average smoothing, which uses the alpha being 0.1. And we use 0.1 because the network, obviously the current estimation can peak just because of the jitter. We can have an unstable system if we would actually make alpha a high value. So that's why we moved forward with this value. We tried others, obviously, but this one worked better and it made more sense to us. And then we had the hysteresis threshold, which just allows us to have a more stable experience. So you're not jumping from 1080 frames to 480 frames in a second, in like glints, probably not even a second. So as you can see in the graph, we would start with whatever. So let's assume that we started with 1080. That's what we start the system with. It's just in the graph. So we start with 1080 pixels, which means we are above the 10 megabytes per second, and that's the threshold that we had. And then once you cross the 480, you change the frame sending to 480. And to avoid having these jumps between the 480 and the 1080, we have this dead zone, which is the retaining zone between the 5 megabytes per second and the 10 megabytes per second. And so if you cross the 4 megabytes per second, yes, you're kind of the 5 megabytes per second. Yes, you are okay to send more, but it's just like a how am I saying? It's just to retain the quality of the experience for the client. You're not seeing like frames jumping. We had this dead zone, so and now once you cross the 10 megabytes, that's when you switch back, just to have this better control on our system. And we had the target playback rate at 24 frames per second. In the client design, obviously the client is responsible of reconstructing the frames, reordering the frames, and the playback. The UDP fragments come unordered and they have to be reassembled. So we get the fragments, we buffer them, and we reassemble them. Once reassembled, we send them to this bounded playback queue, which we allow 10 frames in that queue. And then if you have lower quality frames, those get sent to this optional enhancement that we have here, bicubic FSR-CNN, which is the AI model, and then the FAST API, which is the server side assisted image processing that we have. If we happen to lose a frame, which is very common for UDP, we retain the previous frame just so we for a few seconds, so we don't feel like we have this loss and we don't see that buffering. And then the runtime metrics are being recorded continuously in the client side. That is for our evaluation. So we look over how much time did it take to augment the frame and how much time did it take overall to reconstruct, etc. And then we send the ACK, which is the acknowledgement, with the RTT estimation back to the server with the buffer occupancy, of course, and then we display. So to dive back, how we enhance the model, bicubic interpolation is just a simple way of reconstructing lower resolution frames. So we move from the lower resolution pixels, it estimates the neighboring pixels, and that's how it augments this image. For the local FSR CNN, the convolution neural network, it actually learns what a high quality pixel looks like and it guesses it from the lower ones. The server assisted is doing interpolation, but is also doing filtering and it's doing sharpening. So it's a more advanced bicubic interpolation. So the testing setup, we had two testings in our lab. One of them was the one machine. So just so we have a better estimation, better coordination, synchronization in the time between the two machines. And it just allowed us to have the GPU on both sides, the server and the client. And that's, you can see the data being sent and the client sending back the ACK. The second one was the server and clients being on two separate machines, and that introduced the non-synchronization, asynchronization, and also one of the machines had GPU, the other one was just CPU, while both of them are actually doing image processing and sending, just to evaluate the system better. So this was to mimic in the loopback, which is the same machine, to mimic the actual throughput or like congestion. We added jitter through a uniform distribution that adds latency and independent loss or frame loss or packet loss. And as you can see, the bicubic interpolation by far had the lowest average upscale time. The loss events don't mean that we lost the frame, they actually mean we lost how many lost packets happened. And just because we lose a packet, it doesn't that didn't mean that we lost the actual frame. In this experiment, actually, we were able to retain the frames, just like you saw in the video. We were able to retain the frames, and we didn't lose the perceived continuity of the playing of the video. We can see that the second on the list was actually the server, which had the second lowest upscale time. AI and the CNN obviously had the largest latency, which was expected because it does more to the image. In real network Wi-Fi, we had this in the lab, so it's only one hop. So we had the no jitter, which is just real network, real Wi-Fi, and then we had the moderate jitter, which is adding that latency again. We saw that almost all of them had an average of almost 8 frames per second in the no jitter and almost 5.6 in the moderate jitter. It dropped, but that doesn't mean, but looking at the results, it didn't actually mean it was solely because of the upgrade, but it was more of the decoding, it was packetization, it was reconstruction of the frames. So, and the CPU bounded thing. So it was this combination of the overall system. To analyze our quality of experience, just like we said, we utilized PS on R, peak signal to noise ratio, and the structural similarity index measure. that under moderate network conditions, which is like the changing conditions, to have a better context, the higher the PSNR, the better quality your image is, and the closer the SSIM it to 1 is, the closer your similarity to the actual image. So we can see that local FSR-CNN had the highest PSNR, and all of them had almost 0.9 in their average SSIM, meaning that we had a very good fidelity to the image, which was very good for our system, and we were happy with it. The server enhancement had the lowest average PSNR, and that also goes back into adding into this frame being sent from the client to the server, and from the server of the enhancement, and from the server to the client. So we added more into that overhead of the sending. So trade-offs, looking back at this, we see that we had to choose between quality being sent by the AI, computation, which was very computationally expensive, and the communication overhead from both the server and the client, and then the client to the enhancement server. We see that Bicubic actually achieved the lowest processing cost and fastest enhancement time, with very comparable values in the PSNR and the SSIM. The local FSR-CNN improved the quality, but also increased the computation which was very, like, by far. And the server assisted enhancement kind of balanced between both of them, and then offloaded the actual work from the client side to another machine or server, and maintained kind of a stable latency and an in between. So, as a conclusion, our work, adaptive UDP streaming, is a feedback based bitrate control that offloaded the congestion and network congestion and the throughput being higher. I'm sorry, that was bad, Dr. Otaiba. I'm sorry. But like, it helped our. What was I saying? I'm gonna repeat this one. For adaptive UDP streaming, we tried to make the system feedback based bitrate control with this perceptual enhancement using 3 different modes, which one of them was in AI, and that's how we got to use, and we got good results because all of them allowed us to retain the image and not feel that annoying circular thing, which is very common right now in video displaying. And we looked at this adaptive network and the trade-offs of it, and how our work could set. Probably future work would work on synchronization, especially in the time of the 2 machines, and then maybe explore hardware acceleration, how the GPU affects the work, especially when we use the 2 machines. We can see the CPU bounded one. And asynchronous design, because right now we have a serial design where things move serially, but if we have a parallel design, that would probably lower the processing time. Thank you for your attention. Do you have any questions for me? Thank you. Stop presenting.